The consequences of climate change have become impossible to ignore. In several parts of the world, floods, severe droughts, and extreme weather events show that we are facing an increasingly accelerated global warming. Scientific projections indicate that if we do not drastically reduce greenhouse gas emissions, we will be on a collision course with even more critical scenarios. In this context, thinking about solutions to generate energy in a clean and reliable way has become a priority for governments, companies, and society itself, which watches with concern the rise in extreme events. In this video, we will talk about an alternative that could define the fate of all humanity, so stay tuned. Among the carbon-free energy sources, the most well-known options are solar, wind, hydroelectric, and others less widespread, such as geothermal and biomass. Each of these alternatives brings specific advantages and challenges. Solar and wind, for example, face the problem of intermittency, as they depend on sun and wind, respectively. Hydroelectricity, on the other hand, requires favorable geographic conditions and can be affected by prolonged droughts. In this complex scenario, nuclear energy stands out as a possibility that many consider valuable to complement a clean energy matrix, providing stability and reliability regardless of weather conditions. However, talking about nuclear energy often raises a series of concerns. The mere mention of the term nuclear brings back memories of accidents like Chernobyl and Fukushima, as well as doubts about plant safety and the risks of radioactive waste. Even so, it is impossible to ignore the fact that in several countries, nuclear energy already accounts for a significant share of electricity supply. Globally, this source represents approximately 10% of electric power generation, and in some places, such as France, this percentage exceeds 50%. To understand why nuclear energy can be considered a path toward a clean energy matrix, it is worth revisiting its operating principle. The basis lies in atomic fission. When the nucleus of a heavy atom, usually uranium-235, releases energy in the form of heat, generating a chain reaction. When this reaction is controlled in a reactor, the generated heat heats water, produces high-pressure steam, and drives turbines connected to electric generators. In general terms, it is a method similar to thermal power plants powered by coal or gas, with the difference that, in nuclear plants, the heat comes from atom fission, not from burning fossil fuels. When it comes to climate change, the most evident advantage of nuclear energy is that its operation does not emit carbon dioxide. For this reason, several countries include nuclear energy in their decarbonization plans alongside other clean sources. Some argue that without the stability offered by nuclear plants, many countries would end up relying on coal or natural gas as baseload sources, compromising emission reduction targets. At the same time, critics point to the high initial cost and long construction times of power plants, questioning whether this is the best use of resources, since solar and wind are also becoming cheaper and more accessible. To assess the real role of nuclear energy in the energy transition, it is important to look at the set of renewable sources. Solar energy, for example, has seen a remarkable drop in installation costs. Today, large solar parks and installations in homes and industries are spreading around the world. Wind energy, in turn, benefits from the development of increasingly efficient turbines, both onshore and offshore. Hydroelectricity is already part of the matrix of many countries, but may face issues in climate change scenarios that alter rainfall patterns. And biomass uses organic waste to generate energy. Although there are concerns about the availability of raw material on a large scale without competing with food production. Nuclear power plants, on the other hand, provide baseload energy, generating electricity continuously without depending on weather conditions. In addition, they offer high energy density. A small portion of nuclear fuel can support operations for years, unlike fossil fuels, which require constant refueling. This is where cost-benefit discussions come in. A nuclear reactor requires billion-dollar investments and long construction periods, usually at least 5 to 10 years. However, once in operation, a plant's lifespan can reach 40 to 60 years, with the possibility of even further extension if the structures are modernized and approved in technical inspections. Thus, there is a view that the initial expenditure is spread over decades, delivering a firm form of generation with relatively stable prices, since uranium does not suffer the same market fluctuations as oil or natural gas. In parallel, the management of radioactive waste remains one of the most delicate issues. The fission process generates byproducts that can remain radioactive for thousands of years, requiring rigorous storage methods. One of the solutions under study involves deep geological repositories where barrels containing waste can be isolated by thick layers of stable rock. Countries like Finland and Sweden are close to completing such projects, which aim to minimize any possibility of long-term leakage. Even so, questions persist about how to ensure safety over such extended periods, and there is also the need to obtain consensus from nearby communities, which often raise concerns about possible contamination or transportation accidents involving the materials. On the international stage, mastery of nuclear technology involves considerations beyond the energy sector. Geopolitical and strategic issues emerge as the same technology used for peaceful purposes can, in theory, be directed toward the production of atomic weapons. Non-proliferation treaties and international inspections aim to ensure that nuclear expansion is geared toward electricity generation and other peaceful uses, such as nuclear medicine. Despite this, the global debate over monitoring and oversight remains heated, as there is concern that less transparent nations may use the pretext of nuclear energy for military purposes. Even though certain nations choose not to build new plants, others have shown signs that they intend to expand their nuclear facilities. In Asia, for example, countries like China, India, and South Korea are seriously exploring this source to ensure energy security and reduce emissions, although they are also investing in large-scale solar and wind projects. Germany, on the other hand, has followed a path of shutting down its nuclear plants after the Fukushima accident, although it maintains large wind farms and other renewable solutions. This contrast shows how political, cultural, and historical factors carry significant weight when deciding which energy path to follow. In the current context of climate change, the consensus among most scientists is that all low or zero-emission solutions should be considered. While research progresses on new batteries, green hydrogen, and thermal energy storage, there are also investments in nuclear fusion reactors, which in theory could be safer and generate less waste than fission. However, fusion remains in the experimental stage, and there is no forecast that it will become commercially viable in the coming decades. For this reason, fission continues to be the basis of commercial reactors, and it is on this that improvement efforts in the nuclear industry are focused. Within all this complexity, there is an essential point: the need to quickly reduce greenhouse gas emissions. The Paris Agreement and other international treaties set targets for curbing global warming, and to achieve these goals, each nation faces specific energy choices. In places with space and favorable natural resources, solar and wind can expand rapidly, but they will still require some form of baseload energy or storage system, which can drive up the overall cost of the project. Meanwhile, countries that already have a developed nuclear sector can upgrade their plants or build new facilities to maintain a steady energy supply. This diversified combination may be the most robust way to ensure the necessary electricity supply without relying heavily on coal or gas-fired power plants, major contributors to CO2 emissions in the atmosphere. From this perspective, public acceptance of nuclear energy is an undeniable factor. Even with relatively high safety standards, the fear of accidents and concern over waste tend to provoke intense debates. Many nuclear projects include public consultations before approval, and the transparency of the responsible companies and the government is crucial to gaining the trust of local communities. Some experts also suggest that frequent exposure to clear information on the topic helps reduce negative perceptions based on fear of historical accidents. This does not mean minimizing the risks. On the contrary, having a realistic understanding of the risks and mitigation strategies can make the dialogue more balanced and grounded. From a historical standpoint, nuclear energy has experienced ups and downs. After the emergence of this technology during World War II, many countries invested in harnessing the energy potential of uranium to reduce dependence on fossil fuels. Its peak came in the 1960s and 1970s, when it was believed that nuclear energy could largely supplant other sources. But accidents like 3 Mile Island in 1979, Chernobyl in 1986, and Fukushima in 2011 led to deep questioning about the risks of this type of generation. The anti-nuclear movement gained momentum, and some nations suspended or even banned new projects. Today, however, the urgency of the climate crisis puts the issue back on the agenda, with a more balanced approach to assessing risks and benefits together. Regarding the pace of climate change, some argue that we do not have the luxury of setting aside any clean source already available at commercial scale. In this sense, nuclear energy stands as a viable candidate alongside large wind, solar, and hydroelectric plants, as well as efforts in energy efficiency and the electrification of sectors such as transportation and industry. The fact that it is a concentrated energy source capable of operating 24 hours a day and emits very little carbon throughout its cycle leads governments to seriously consider building or maintaining reactors, even in the face of criticism over costs, safety, and waste. On the other hand, it cannot be ignored that the adoption of nuclear energy depends on each country's context. Some have an abundance of sunny areas or constant winds, which facilitates the expansion of renewables without needing to resort to other options. Others have limited territory and less favorable weather conditions, but possess the financial resources and technical capability to build nuclear power plants. There is also the political factor. Governments and populations may reject the idea of radioactivity, even though, statistically, the risk of accidents is low, and the history of direct deaths linked to nuclear energy is smaller when compared to the impacts of pollution generated by fossil fuels. In the end, the relevance of nuclear energy in the context of climate change has less to do with sensationalism and more with the realization that we are facing a planetary challenge. Reducing carbon emissions on a large scale requires a combination of solutions, each playing its role. Nuclear energy should not replace all other clean alternatives, but it can be integrated into a hybrid matrix, helping to balance supply at times when solar and wind do not generate enough. At the same time, scientific research remains open to new discoveries, improving uranium mining and enrichment processes to reduce emissions, making reactors safer, designing better waste storage facilities, and in the future, making nuclear fusion viable. The climate urgency forces society to make complex choices. While some countries ban nuclear, others are betting heavily on it as a key part of their decarbonization strategy. Many of these decisions also reflect cultural and political factors, since the fear of nuclear accidents is deeply rooted in the collective imagination. In addition, economic variables carry weight. Planning a nuclear plant involves long timelines, high investments, and financial risks, even though the return may stretch over decades. Renewables like solar and wind, on the other hand, are simpler to install on a smaller scale, with shorter deadlines and increasingly competitive costs. Given these scenarios, the keyword for many experts is complementarity, using the best of each source to build an energy system that is clean, safe, and economically viable. In this scenario, nuclear energy enters as a pillar of stability, ensuring continuous supply and reducing dependence on fossil fuels, while renewables occupy an increasingly larger space in the generation mix. With efficient regulation, strict safety standards, and public awareness of the risks and benefits, nuclear energy can play a relevant role in the fight against global warming without being treated as the only answer to the challenges we face. For this reason, when analyzing emission data and the rapid melting of polar regions, there is growing understanding that on a global level, failing to explore nuclear energy could mean missing out on a valuable resource in tackling climate change. Of course, each nation will decide whether this path makes sense in its context, but the strategic importance and low-carbon potential make the discussion inevitable. In the end, the choice between nuclear and other clean sources doesn't have to be exclusive. The climate crisis is urgent, and what matters is combining forces to quickly reduce emissions. In this way, nuclear energy emerges as a realistic ally on a planet that cries out for effective and immediate solutions, even though its limitations and challenges cannot be underestimated.